It remains to prove the first step, that if we have an arbitrary distance function, then it's possible to map the vertices to some high-dimensional vectors, such that when we compute the summation over the g edges of the distances in L1 of the endpoints of the edges, divided by the summation over the h edges of the L1 distances of the endpoints, this is at most order of log n times the summation over g edges of distances according to the original distance function of the endpoints, divided by summation over the h edges of the original distances. We will prove this via a theorem of Bourgain from metric geometry that says that for every distance function that satisfies the triangle inequality, it is possible to find a mapping of vertices to vectors such that the distances according to the given distance function are the same as the L1 distances between the vectors that we construct up to a logarithmic approximation term. Once we have such a theorem, and once we have a constructive proof of such a theorem, that given the matrix of distances will give us in polynomial time the actual mapping of vertices to vectors, then we are done with that step, because when we look at this expression, we can see that each distance in the numerator can be upper bounded by the corresponding distance duv, and every distance by this side of the inequality, and every distance in the denominator is at least 1 over log n times the corresponding distance here by using this inequality. And it is in this step of the argument that we make the transition from what we get out of the linear program, which is an assignment of distances between pairs of vertices, to something that instead is a function of individual vertices. So how do we pass from a distance function that gives an assignment of distances to pairs of vertices to a distance function that is based on assigning one vector to each vertex? A common method to map more generic distances into L1 is through what is called a Frechet mapping. This is based on the following idea. Suppose that we pick a subset of the points on which we have a distance function defined, in our case a subset of the vertices of the graph. And then we define the following function. For every vertex, we look at what is the distance of the vertex from the closest point in the set. This could be 0. And Bourgain's argument is that it's possible to find a distribution over sets such that up to an error of log n, the distance between 2 points are the expected differences between this function fa applied to u and the function fa applied to v. Here the expectation is over the choice of the set according to the distribution defined by Bourgain. Now this is not quite what we're looking for, because we're not defining a deterministic embedding of vertices into L1, but we're defining a probabilistic mapping of vertices to real numbers. However, the two are equivalent, meaning that suppose we have some distribution d over real functions, and suppose that this distribution has a finite support. Then there is a deterministic mapping of vertices into vectors such that the L1 distance according to this deterministic mapping is precisely equal to the expectation of the difference between fu and fv, where this expectation is taken over random choices of a function f from the distribution D. And this is very easy to prove. You just construct f so that it has one coordinate for every point in the sample space of this distribution. And what you see in that coordinate is the corresponding function little f, with all the entries scaled by the probability that that particular function little f is sampled according to the distribution D. So then it's just a one-line calculation that the L1 distance will just be the expectation of these differences. In fact, the perspective of an L1 embedding being a mapping of vertices into vectors of which we compute the L1 distance, and the perspective of having a probabilistic mapping of vertices into real numbers for which we compute this expectation of differences, those are completely equivalent viewpoints. And in order to describe Bourgain's theorem, it's easier to use this perspective of a probabilistic mapping of vertices into real numbers. Now, why do we prove it by using Frechet embeddings? There is a big advantage of mappings that use Frechet embeddings, which is that automatically, no matter how you choose the set A, this difference FAU minus FAV will be at most the distance between U and V. And that's easy to see. If this is the set A, and now we are looking at two vertices U and V, then U is closest to some vertex A in A, and V will be closest to some vertex B in A. A and B could be the same vertex. So the distance between U and A will be, and the distance between V and B will be FA of V. But now FAV has to be smaller than the distance from V to A, because V must be closer to B than to any other element of capital A, including small a. And by the triangle inequality, the distance to go from V to A according to the distance function D cannot be any more than the distance to go from V to U plus the distance from U to A. The distance from U to A being FAU. So this shows FAU minus FAV being smaller than DUV. Now you just repeat the same argument but with the roles of U and V reversed, and you're going to get FAV minus FAU smaller than DUV, and so you have the required inequality. If this inequality is true for every set A, it also means that no matter how we pick a distribution over sets A, this expectation will be at most DUV. So when we want to show that this expectation is an approximation of DUV, we immediately have the upper bound expectation being smaller than or equal to DUV, so we just need to focus on this lower bound.